Hey everyone, how we doing? Pretty good. 8:30 a.m. on the last day of reInvent. I'm actually surprised you folks turned up, so thank you. We have a whole bunch of content here for you folks, and it's a little hard to see you folks because of the lights and whatnot, but we'll kind of work through here and kind of press on. So this is Net 206. Advanced Amazon VPC design and new capabilities. They actually changed the name on me this year, so it's a little bit different. But the idea of this session is we're going to dive into all of the changes that we've done over the last 12 months, all of the new features we've released, and it is a 200 level session. We'll talk about that. I'm Matt Lewis. I'm a Principal Solution Architect here at Amazon Web Services, and I have a co-presenter today, Alex Hudesh, who is a Senior Networking Specialist Solution Architect at AWS as well. Welcome, Alex.
Nice to have you here, thank you.
All righty. So we have some housekeeping items to start with. First up, there's some QR codes in the session, so feel free to take photos of those. They'll take you to links with more information about each of the services that we're going to talk about. We've also got our work from home networking wizard who's going to pop up throughout the session, and he'll have some helpful hints for you folks about each of the services. Also, I'm doing a networking wizard session coming up in about an hour and a half as well. Feel free to join that. And lastly, we have a bunch of architectures in this session. And so it is advanced VPC design, and we talk about a lot of the architectures and how they're put together. The beauty of networking is it's really easy to build networking architectures in PowerPoint and kind of convey what the traffic flows look like for a lot of these architectures. And as network folks interested in VPC, this is immensely useful. However, we have a lot of build-outs, so we do throw a little camera icon up there when those are finished, so you know when to take a photo if you wanted to. Again, this is Net 206. A bit of a disclaimer, we do jump around a lot as far as the leveling goes in this session. 200 is probably not where we're at. Sometimes we're at 100 level, so bear with us if you're more advanced. And sometimes we might dive into 400 level just because of the nature of the topic. Okay, so for the last 12 months, we've been up to a whole bunch. Alex and I have become experts in baking, like a lot of other folks. We've been having a lot of fun. But what we're actually going to do right now is step back to reInvent last year, December, November-ish, and talk about what AWS architectures looked like at that point in time. And so this is where we do a little bit of 100 level stuff and kind of start building upon that. So a VPC in general is a region level construct. And within a VPC, you've got things like a CIDR range. You can expand that range. You can use IPv6 in a dual stack mode. We have availability zones within our VPCs, or within our regions for the VPC. We have subnets, and then we have EC2. So EC2 runs inside of VPC, and again, this is our base level 100 level stuff here. And so we have services that sit inside the VPC and services that sit outside the VPC, and we'll talk about those and the connectivity between those services. We also have the public internet. We'll talk about how to connect to the public internet. Now, in this case, again, back in December last year, we'd essentially have route tables like we do today, and you can send traffic to what's called an internet gateway and connect to public services using a default route to that internet gateway. You might also use maybe an NAT instance if you're willing, or you might be using NAT gateway. And again, we'll go a little quick here because this is kind of our base level stuff. And so as we build this out, we can use things like gateway endpoints to connect to S3 and DynamoDB. We can use a VGW or virtual private gateway to connect via VPN to on-premises, or maybe even Direct Connect and Direct Connect Gateway. We're going to talk about Direct Connect Gateway in this session as well. There's some exciting stuff coming there. We can peer VPCs together, either inside the region or cross-region. So if you want point-to-point VPC connectivity, you can do that. And then we have Transit Gateway, which is an immensely powerful service that can connect up to 5,000 VPCs in a single region. And so you can have multiple transit gateways. We've got a whole bunch of transit gateway architectures that we're going to chat about. You can also do cross-region peering for transit gateway. You can connect to your on-premises via what's called a transit VIF via Direct Connect, or you can use VPN as well. We have flow logs, if you want to get some metadata on the traffic traversing through your network. And again, that camera icon will come up shortly when this build-out's finished. We've got a little more to go. You can use interface endpoints and private link to build services to drop privately into a VPC, another very awesome service. You can also connect privately to many other services. Last I counted, it was almost over 100 services that we could connect to privately via private link. We have Global Accelerator, which is like an Anycast-like service with a whole bunch of other features built into it. We have traffic mirroring if you wanted to get packets from your instances and inspect those packets. You can send that to an NLB or an EC2 instance. We have gateway route tables where you can basically say traffic coming into the VPC can get directed via something like a firewall. So we've got a firewall here in one of our public subnets. We then released last year, this was a new service, Gateway Load Balancer, which basically helps with putting things like firewalls in line. So now you can have a dedicated VPC as an inspection VPC and use a Gateway Load Balancer to have a scalable firewall edge in front of your VPC deployment. We also have client-to-site VPN, AWS Outposts, which extends AWS, the VPC, all the way down to an on-premises that you choose. And so basically, if you have a data center, you can deploy a rack and have VPC running at that rack. And then lastly, we have AWS Network Firewall. Now, Network Firewall is not in the right place here. It's in the middle, but it actually runs inside a subnet. But last year, we announced AWS Network Firewall, which is similar to Gateway Load Balancer, but allows you to have a network firewall in line for your traffic inside the VPC. And so as of December last year, and there's our camera build out, as of December last year, this was how you would build your VPC architecture. So customers would have some of this, all of this, a combination of, and we're going to dive into a lot of the architectures that you can build today and a lot of the changes. So first up, what else have we been up to for the last 12 months? And Alex, I'll let you take it away from here.
Thank you. Well, IPv6 is the protocol that I think we've all been waiting for more than 25 years now. And we've been pretty busy in this space, pun intended. Let's start with IPv6 only subnets and IPv6 only instances capability that we've recently launched. We're going to start from our dual stack native AWS VPC, which by default has a primary IPv4 CIDR, and we can add an IPv6 CIDR to it, making it dual stack. IPv4 only subnets and instances can coexist with dual stack ones. Starting from this, we can add IPv6 only subnets to our deployment now. What this means is that we can start spinning up EC2 IPv6 only instances, and we can expand beyond the limited capabilities of the IPv4 private space. Now, our VPC is going to continue to be dual stack, okay? So we're only going to have IPv6 only subnets part of the VPC. We're interested in seeing traffic flows. And first, let's start with the traffic flows inside the Amazon VPC. Whom can our IPv6 only instance talk to? Well, it can talk to other IPv6 only instances and resources in the VPC, and with dual stack instances natively without any additional configuration needed. I know you're wondering about the IPv4 reachability from the IPv6 only instance, and we're going to come back to this flow in a second. But before that, let's understand internet connectivity, especially for private subnets to begin with. In the dual stack world, we have IPv4 and IPv6 resources in dual stack or IPv4 only subnets. For the IPv4 stack, we do need, because IPv4 addresses are private, the elastic IP addresses for public resources and public subnets. For dual stack, we have the same capability in the IPv4, but for IPv6, native connectivity is ensured with the internet resources because of the fact that IPv6 addresses are globally unique and routable. So no elastic IP addresses are needed. Now, for our IPv6 only subnets and instances, the same construct is kept in public subnets. We use the internet gateway to reach IPv6 enabled internet endpoints. I know you're wondering again if this flow is possible or not. Let's have a bit of patience. Because we also need to look at private subnets internet connectivity. The way in which it worked for IPv4 and dual stack is that in the IPv4 stack, we do need the public NAT gateway for IP address translation. So in the IPv4 stack, we're using this NAT gateway. For IPv6, though, we do not need translation, but we do need to keep the same security posture for our private subnets. So we use the egress-only internet gateway to ensure that only outbound flows are enabled towards internet endpoints, and there is no capability for internet endpoints to open connections to our private subnets IPv6 addresses. Just a quick call out here for us to remember that the EIGW has this capability to maintain the same security posture. Now, for IPv6 only instances in private subnets, we keep using the same egress-only internet gateway. No NAT is needed, and the IPv6 only instance is able to open those connections to the IPv6 enabled endpoints in the internet. And yes, time has come to talk about that IPv6 to IPv4 backwards compatibility with the help of NAT64 and DNS64. And let's see why we do need both. These are the two flows that we were wondering about inside the VPC and with the internet. How can we use them? Well, before we go there, in the VPC, the native DNS resolution happens with the help of the DNS resolver in the VPC. If the IPv6 only instance would query about an IPv4 only endpoint, and it would receive an IPv4 address, it wouldn't know what to do with it because it's not enabled for IPv4, right? So what we can do is enable DNS64. This is a subnet level setting, and this allows the IPv6 only instance to query the dual stack resolver endpoint for the IPv4 only endpoint and to receive a synthesized IPv6 address with the help of the well-known prefix 64FF9B created from the IPv4 address of the IPv4 only endpoint. In this case, the IPv6 only subnet says, okay, I'm all good to go. I can generate this IP packet. But question is, if the IPv6 only subnet instance generates that packet, how is the IPv4 only endpoint going to be able to interpret that? It's not going to be able to read IPv6, right? So traffic needs to go through the NAT64 gateway to be translated from an IPv6 packet to an IPv4 one. How this works is exactly like that. Traffic goes from the IPv6 only instance through the NAT64 gateway and is translated into an IPv4 packet. Now, let's see what the traffic flows are for this. Just a reminder, NAT64 is automatically available on all NAT gateways that you already have in your environment and on all new spun-up NAT gateways. It's not a setting that you enable. So traffic flows. We can start talking right now with IPv4 only resources in our own VPC, with internet IPv4 only endpoints, and with our private IPv4 endpoints in our private network. Now, what about DNS in the VPC? Well, what about it? We have the new capability of resource-based naming in the VPC. Up until recently, the way in which instances were named in the VPC was with the help of IP-based name. The VPC DNS resolver has a hierarchy that uses to reply to DNS queries in the VPC, private DNS, VPC DNS, and public DNS. When an instance in our VPC would query for an IP-based name, it would receive the IPv4 address, private IPv4 address associated with that. Now, our IPv6 only instance has to have an instance name, right? Has to have a DNS name in the VPC. What is that? Well, resource-based naming is the way in which IPv6 only instances are named in the VPC and is a subnet setting level that is by default enabled for IPv6 only subnets and can also be enabled for IPv4 subnets and dual stack subnets for consistency in our environment. So what happens now is that whenever a query comes to the DNS resolver with an instance-based name using the instance ID, the DNS resolver will reply to either the A record or the quad A record to that query. Now, last but not least, we've seen how we can deploy IPv6 only instances and subnets. Let's see how we add scalability to that environment with the help of elastic load balancers. And we're going to start with our enhanced Amazon VPC dual stack VPC with IPv6 only subnets. And we're going to see what the capabilities of application load balancers and network load balancers are. Starting with the application load balancer, when we deploy it, we have to specify from the networking perspective the load balancer subnets, the type of load balancer, if it's an internal or an internet-facing one, and the targets. So far, we were supporting internet-facing dual-stack application load balancers. That means that the load balancer was in a public subnet and had IPv4-only targets. What we've recently launched is the ability of deploying internal-facing application load balancers, which means that the load balancer subnets are private, and the ability for dual-stack load balancers to target IPv6-only instances. Now, network load balancer has the same capabilities. When we deploy it, we have to specify the network load balancer subnet, the type of network load balancer, and the targets. We were supporting internet-facing dual-stack load balancers. That meant that they were deployed in public dual-stack subnets, and they were targeting IPv4 addresses. Now, we've launched the internal dual-stack support for load balancers. That meant that private load balancers were able to be dual-stack, and the ability for them to target IPv6-only subnets. Quick note here, for both ALB and NLB, IPv6 targets need to be IP type, and they need to be in a VPC, in the same VPC or in a peered VPC. Now, let's put everything together. And starting from our initial dual-stack VPC with IPv4 and dual-stack subnets, we've added the IPv6-only subnets. We have the dual-stack endpoint resolver in the VPC. We have IPv6-only instances with resource-based naming enabled. We have DNS64 and NAT64 to facilitate communication between IPv6 and IPv4. We have internet routing and private network routing with transit gateway and VPC peering and VPNs, dual stack natively enabled. If you want to know more about IPv6, please scan the QR code and read our IPv6 white paper.
All right. I mean, that's a whole bunch of IPv6 stuff that we've been up to for the last 12 months. How old's IPv6 now, 25 years or something?
25 years, yeah.
Okay, so we've been waiting a long time to get IPv6 support for things like IPv6 only subnets. And some of the stuff I've seen when talking to customers, it's not just public IPv6, it's private IPv6 as well. So customers that are using AWS and have a large on-premises deployment run out of RFC 1918 or private addressing and really want to be able to use v6 native subnets within the AWS deployment. So really excited, really awesome stuff for IPv6. So I should have said this at the start. We'll take questions at the end. So feel free to come up and we'll have a chat about that. Yeah, no problems. So the question just quickly was, do we have control over the IPv6 addressing? And you can bring your own IPv6 addresses to AWS, or you can use AWS's IPv6 ranges as well. This leads us into talking about IP addresses, IPAM, or Amazon VPC IP Address Management. This is a brand new service that was just launched. I believe it was yesterday or the day before?
Wednesday.
Wednesday. All the days kind of run into one day here. It's a busy week. I'm sure you folks have seen something like this before. This is basically an Excel spreadsheet or a table that has IP address allocations. I've worked in large mobile providers, large telco providers, and we've literally used an Excel spreadsheet that's on a shared drive to allocate IP addresses. There's some problems with that picture. So first, it's manually updated. We used to have one guy, the firewall guy, who had ownership of all the IPs, and you'd go to this guy and say, hey, his name was Kieran. Hey, Kieran, can I please have an IP address range? And he would go in and update the Excel spreadsheet. Manual updates are not scalable. You also have limited visibility into who's using what. I mean, it's just a table, it's just a spreadsheet. Also, ability to manage allocations at scale. We have customers that have over 1,000 VPCs. Can you imagine allocating 1,000/16 ranges for your VPC use, or maybe smaller, or multiple IP ranges per VPC, and then managing your on-premises as well? So now we have Amazon IP Address Manager, or IPAM. And basically, IPAM allows you to have automatic IP assignments. So you can basically allocate IPs automatically to VPCs. You can monitor across your networks the usage of IPs. And you can do things like retrospective analysis of IPs. And we'll talk a little bit about the historical data that you can look at on where an IP has been, what it's been allocated to. And so a key point here is it works for v4 and v6. So that's great. So we've been doing a whole bunch of stuff for v6. Of course, we needed to support v6 for IPAM as well. Now, what it basically looks like is you have when we'll talk about scopes and pools and the different components that make up IPAM, but you basically have this hierarchical topology where you've got a top-level pool that you allocate IPs from for sub-level pools in regions, and I'll talk about that. You can also set business rules for your application, so which accounts can use which IPs, which regions can use which IPs, so there's a little bit of policy control there around who can actually consume those IPs. You can also have developers create VPCs and request IPs as they go. So no longer do they have to go and see the guy or girl managing the Excel spreadsheet and say, hey, can I please have some IPs? They can do that automatically. We also have a single dashboard that you can monitor your IPs from, and I have a couple of screenshots on what that looks like too. Sorry, I'll just pause there for a second. I know some folks were taking a photo of that one. Feel free to. Okay, so let's talk about some of the key IPAM components. So first we have a scope. A scope is basically, you can think of it like a network or a group of connected networks. So basically, you can reuse IPs across those networks, or unconnected networks, sorry. We then have a pool, which is a contiguous block of IPs within the scope itself. So when you create an IPAM, you'll actually have two scopes that are created by default. You have a public scope and a private scope. And that's because you've got public addresses, which are obviously different from private addresses. So they're different unconnected networks. Within each of those scopes, we'll create pools as well, which you can then allocate out your IPs, and we'll talk more about pools. You can also set a refill policy so that if you have a top-level pool, it can refill some of the sub-level pools from itself when you start running out of IPs in those sub-level pools. And you can also create an allocation policy as well, so you can enforce business rules across your addresses for your different business units and such. Let's jump in and check out the console though. Excuse me. Okay, so here we are in the VPC console. And what we want to do is go up and click Create IPAM. This is actually pretty straightforward. Generally, you can only have one IPAM per account. And so to create the IPAM, first up, you're going to want to tick this box here to allow us to replicate data from the source accounts into the delegate IPAM account. And this is just something that we need for the service to run. Then we're going to go down to the name and description, pretty straightforward here. So you'll set a name, and that'll by default create a tag for the IPAM itself. You can set a description if you want. And then the next thing, and one of the most important things here, is you need to define the operating regions for IPAM. So we're actually just going to select all regions, but for IPAM to work across regions, you need to allocate what regions it will be allowed to work across. And so we just enable all regions here, just because we want to make it easy for ourselves. And then you can set some tags if you want as well. So the name is just a default tag that pops up there. Now within the IPAM console, you can see that we've actually got an IPAM. If we jump in and have a look at that, you'll notice that we've got the two scopes that I mentioned earlier, the public scope and the private scope. So for your public addressing and your private addressing. Now, what we'll then want to do is go over to the left-hand side here to pools and create some pools that we can allocate addresses from. And so within the pools themselves, you can see some of the configuration components here. So you can basically create a pool hierarchy. So what you'll probably want to do is, actually I have a slide on this next, I'll save that. You'll create a pool, but you'll allocate CIDRs to that pool that you can then allocate from. And so pretty straightforward. After we've created the pool, we can then start allocating IPs. However, as an example, if we look at, say, a private scope here, we've got a top-level pool that might have a /8, so a 10/8. So we've got a lot of IPs that we can use here out of this pool. We then will jump into each of the regions, or we'll create a pool for each of these regions. So we'll create a 10/10, 1064/10, and a 10/128/10. As we kind of go along within each of the regions, we might create a dev pool and a prod pool, so sub-allocated from those region-based pools. So you'll notice we're building this hierarchy now for allocation of IPs. Now, each of the VPCs in each of those regions can then pull IPs or have allocated IPs from each of those pools, from the dev pool or prod pool, as we kind of go along. And you'll notice those IP ranges are from each of the pools that they're being allocated from. So pools are basically a hierarchical topology where you're creating this sub-level or this top-level pool and then creating sub-pools from that. Now, IPAM wouldn't be IPAM if we didn't support Bring Your Own IP. Bring Your Own IP is something that's been around for a while in AWS, and basically it's the ability to bring public IPs or IPv6 addresses to AWS that you own, and you can then use those within your deployments. Now, essentially what we've done is we've brought Bring Your Own IP and IPAM together, so we support Bring Your Own IP. So that improves your IP address allocation across your organization. So what it basically looks like here is without IPAM, you would bring an address range to an account. And so within that account, you would then deploy a VPC or use those public IPs from your public pool, et cetera. But you'll notice here we've got different utilization in each of the accounts because each account has its own pool. Now, when we start using BYOP with IPAM, you can actually bring the IP range to the IPAM account and then allocate those out using the pools to each of these other accounts. And so what that basically does is it gives you a better utilization across your deployment across AWS so that you're not basically bringing an IP range to every one of those single accounts anymore. And so we do allow you to migrate existing BYOP IPs to IPAM. We have a simplified onboarding process, and we do enable both internet and IPv6 for Bring Your Own IP with IPAM. Okay, we have a really quick view here. Sorry, the screen's a little bit small here, but within IPAM monitoring and alerts, you can see the utilization of each of your pools. So you'll see here we've got 1 million provisioned IPs, and we're sitting at roughly around 25% utilization. So you can jump in and have a look at some of the reporting within the console itself. Now you'll notice here we can see a bit of historical reporting on our utilization of the pool. So this stuff is really important to have some visibility into how many IPs do I have left. And again, like I mentioned, those companies that are running out of RFC 1918 addresses and need to have some visibility into their allocation and usage of these IP addresses. And we also have a bit of a view here for compliance. So based on tagging, we've actually got a non-compliant IP where the allocation policy doesn't match the IP that's been allocated. So there's a bit of policy control there around the allocation of the IPs themselves. And lastly here, some historical insights. So the idea here is giving you the ability to have a look at the life cycle of an IP. So when it was associated with an instance, when it was disassociated, when it was overlapping with another IP. And so you can go back and have a look at some of the data there on that. And so that leads me to the end of IPAM. Quick QR code there if you folks want to learn more about IPAM. For me, deploying AWS environments and deploying many VPCs, I think IPAM is just one of those things that it just makes sense to use. I mean, there's no reason why you wouldn't want to use IPAM. I mean, going from a table or a spreadsheet or a text file, which I use sometimes, IPAM just brings so many more features to the table. Alex?
Thank you. Well, now that we don't have to worry about IPAM anymore, we do have the solution. Let's start focusing a bit too on the Amazon VPC networking and the innovation that we brought in this space. We're going to start with enhanced VPC routing. What that essentially means is that we can override the local routes in the VPC route tables with more specific routes. Where this comes into play a lot is when we are trying to create inbound inspection architectures or east-west inspection architectures. What we could do before was, with the help of the internet gateway and the ingress routes on the internet gateway, we could redirect the traffic that was destined for a public resource in a public subnet to an inspection subnet, where we could make use of AWS Network Firewall or Gateway Load Balancer or any other third party that you would want to use there to inspect that traffic that would go to the public subnet and then further down to backend. Now, the return traffic needed to keep the same path, so routing had to be configured accordingly. What we can do now with more specific routing is move from inspecting only inbound traffic into the VPC to having the ability of inspecting traffic between subnets of the same VPC. So now we can redirect that traffic that would go by default between subnets directly according to the local route through the inspection endpoints. Now, one quick call out here to keep in mind is the fact that we cannot have CIDRs for more specific routing different than the subnet CIDRs that we have in the VPC. So we can more specifically route subnet CIDRs. What this enables us to do is also create a sort of service chaining. So we have inspection at different levels, both at the ingress from the internet gateway towards the public endpoints, and also between our application and database. All this traffic goes through the inspection endpoints and is inspected differently depending on the layer that we are doing it at. Now, the second focus topic is private NAT. And I know we've talked about IPv6 and the ability to enable IPv6 to overcome the limitations of IPv4 private space. But still, there are challenges with overlapping IPv4 space in the VPCs. So how can we enable those overlapping IPv4 spaces to talk to resources in our environment with private NAT? Till recently, the private NAT, the NAT gateway was dependent on the internet gateway. So when we wanted to deploy it in the VPC, we would put it in a public subnet, and what it would do is to actually translate the traffic that was coming from the private subnet instances into its own private IP address that was mapped to an elastic IP address at the internet gateway level. With private NAT, that dependency is removed. You can enable, you can deploy in your VPC private NAT gateways without the need of having internet gateway. And what that enables is just the translation between two different private IP addresses. Let's look at a traffic flow and how can we enable two VPCs with overlapping IP space to talk with the shared services VPC first, right? We have resources that need to be accessed centrally from all our VPCs in our environment. What we do is add a non-overlapping IP space to our VPC and spin up that private NAT gateway in the non-overlapping space. With the help of transit gateway connectivity and the appropriate routing in place, we get those traffic flows to the shared services VPC from the overlapping VPCs in our environment. Now, the same functionality is enabled towards private environments on our own premises. So you can use private NAT gateway for the same type of traffic flow from VPCs with overlapping IP space towards your on-prem in this case. Now, a very important call out here is the fact that private NAT gateway does not enable bidirectional connectivity between our overlapping IP spaces in our VPCs. What we need to do for that is spin up elastic load balancers, or a way of exposing those services in the non-overlapping space in our VPC. Our third focus point is AWS Private Link. And what AWS Private Link historically enables us to do is privately access AWS services in our VPC by bringing them with the help of VPC endpoints. We have two types of VPC endpoints, the interface endpoints and the gateway endpoints. And we can make use of Private Link as well to expose our privately maintained services to other VPCs in our environments. So we can become the service providers for certain services. Now, no additional routing is needed, so this is a powerful tool for exposing or accessing AWS services or custom maintained services. I mentioned that there are two types of endpoints, the interface endpoints and the gateway endpoints. S3 and DynamoDB historically made use of gateway endpoints. So how gateway endpoints work is that they do not require but routing towards the endpoint from the VPC, and they cannot be accessed from outside of the VPC because they are just routes in the route table. Now, with the added functionality of S3 interface endpoints, we keep the same architecture for gateway endpoints, so nothing's changed there. We can continue accessing S3 from the RVPC privately through the gateway endpoint, but we can also bring S3 in the VPC with an IP interface, right? So having an IP address for this enables us to access S3 from outside of the VPC on a private IP address. Now, I mentioned at the beginning of this section that there are two types of services we can access with Private Link AWS services, or we can maintain our own services. And we've listened to feedback from customers that said, okay, we have services that need to be front-ended by AOBs. So we've brought AOB support for Private Link through the integration of NLB. What this means is that what we could do so far was have our service provider service front-ended by an NLB with the use of an endpoint service and VPC endpoint we would expose that service to client VPCs. And now, with the native integration between NLB and ALB, we can actually have integrated with PrivateLink those ALB front-ended services. One could call out here that we do recommend to match ALB and NLB subnets and availability zones, and both the NLB and ALB need to be in the same account. Our last focus point is going to be Transit Gateway, and the two added functionalities that we've launched this year, Transit Gateway Connect and intra-region peering. But before that, let's look at what Transit Gateway gives us. Transit Gateway is the routing hub in AWS that enables highly scalable connectivity for thousands of VPCs in AWS, allows integration with AWS VPN, with Direct Connect, with Direct Connect Gateway, and the Transit Virtual Interface, allows the integration of the global network with Transit Gateways in multiple region and cross-region peering, and the integration with environments that were previously deployed in AWS with Transit VPC, as well as inspection architectures, both for inbound and outbound inspection architectures and east-west inspection. Now, what Transit Gateway gives us is the integration between our AWS environment with Transit Gateway and SD-WAN appliances. This makes use of two types of transport attachments, the VPC attachment or the Direct Connect Gateway attachment, on top of which we can create the Transit Gateway Connect attachment. This Transit Gateway Connect attachment allows us to define connect peers on top of it, which are GRE tunnels, generic routing encapsulation, with BGP sessions, allowing the Transit Gateway to exchange routing information with the SD-WAN appliances. Now, I mentioned two features. First one, Transit Gateway Connect. Up till recently, actually Wednesday, I think, we could peer Transit Gateways together across regions. So we could have that global routing environment in AWS. What we've launched, and we've listened to the feedback from customers, is intra-region peering. And you would ask yourself, why do I need that? Well, besides of the fact that it works the same, so no special configuration is needed, it allows you to create hierarchical architectures and to integrate acquisitions. These are the two big use cases for intra-region peering that we've seen our customers want. Imagine you're a company and you already have your global infrastructure in AWS, you have Transit Gateways in multiple regions, you have hybrid connectivity. Now, with acquisitions, the need arises to integrate those acquisitions to the existing network, to give those services access to shared services. You want to have the ability of integrating that seamlessly, and that happens with intra-region Transit Gateway peering. The second use case is hierarchical architectures, and this is driven either by security limitations or standards that the company needs to abide by, or the need to separate the domain of operations. So with separate prod and dev transit gateways, for example, you can have core transit gateways that offer cross-region and global connectivity. This looks a bit familiar with the data center hierarchical architecture, if I remember that. Matt?
All right, thanks, Alex.
Take us to the future.
Yeah, so intra-region peering for Transit Gateway, I've been waiting for that one for a while. I felt like when Transit Gateway first came out, I wanted to jump in and configure that straight up, and we actually only had cross-region peering, so that's actually a great one. So let's talk about on-premises and global connectivity. So we'll start with Direct Connect, and we'll talk about things like MACsec and 100 gig connectivity and local zones. But first, before we do, we're also going to do a bit of a baseline check here on Direct Connect. So Direct Connect is essentially a service that allows you to connect your on-premises through to AWS via a direct fiber connection. And so if you've got a data center, you may have a service provider network or something similar. and you would want to connect to what we call an AWS Direct Connect location or a point of presence. And at these points of presence, we have physical routers that we've deployed, AWS has deployed, that you can plug fiber into. And so you'll probably have a customer or user partner's cage or partner connection or something similar at that location. And then you'll connect what's called a cross connect, which is a physical fiber from that partner device or your device in that location to the AWS port. Now, Direct Connect actually has a per port per hour charge, because what you're essentially doing is almost leasing the optic inside the physical device that's at our location. You're plugging a fiber into that optic and it's yours. You're using it, a 1 gig or a 10 gig, unless you use a partner's connection. So then we have the AWS region over here on the left-hand side. And with Direct Connect, you can essentially build a public virtual interface, which allows you to connect to public services, or you can build a private virtual interface via what we call the VGW, we touched on a little bit earlier, and have a private connection directly to your VPC. So now you've extended the VPC all the way through to your on-premises. What you can also do is have up to 50 virtual interfaces per Direct Connect. So you could connect to up to 50 public or 50 private VPCs if you wanted to. And in this case, we have 2 private virtual interfaces connected to 2 VPCs. So what we did back in, I think it was 2018, or it might have been 2017, we released AWS Direct Connect Gateway. And Direct Connect Gateway is essentially, it's one of our few global services, but it operates globally across all of our regions and allows you to connect a single private virtual interface, in this case, to multiple VPCs. Now, in a lot of cases, you could have those VPCs in the same region, or you could split those out and connect to other regions. So with Direct Connect, there's this concept of having a Direct Connect POP location homed to a region. And that's where you could send a private VIF and connect to private VPCs. With Direct Connect Gateway, you plug into the Direct Connect Gateway, you on-ramp onto our backbone, and then you can connect to other regions as well. And you actually don't trombone through the local region. So you're going to use a fast path or our on-ramp and network to connect to other regions as well. So that's Direct Connect, really quick overview. Now we also have MACsec availability for Direct Connect. So there's a saying we have here in AWS, I don't know if we coined it or not, but dance like nobody's watching and encrypt like everyone is. So we're doing a lot of encryption within the region, so using things like our Nitro system to encrypt instance-to-instance communications. Going from a Direct Connect POP location to your router is not encrypted. It's a fiber. Someone, could be providing that fiber to you, like a third party, the data center provider. So MACsec allows you to encrypt the traffic between that POP location and your physical connection. And so basically MACsec operates at layer 2. So it's going to allow you to encrypt things like ARP, DHCP, BGP, anything that's operating at those upper layers above layer 2 for that connection. It's also high-speed connection. High-speed encryption. If you look at an IPsec connection, IPsec within AWS, you connect to a VGW, you can get 1.25 gigabits per second per IPsec connection. If you built an instance inside a VPC, you would also get about 1.25 gig, depending on whether you use jumbo frames or not. Part of that is because IPsec is actually being processed within the CPU itself of the instance. So it's a long story, but essentially IPsec is pinning to a CPU process and is requiring some operations there. When we look at MACsec, it's actually a hardware level process. And so we can offer, or MACsec offers, far greater high-speed encryption between those two devices. And so essentially it would look something like this. On the customer side, your side, you would have a MACsec capable device. You could take a router that's not MACsec capable and put a MACsec capable switch or something similar in front of that router if you wanted to, but then you would connect via the cross-connect into the AWS router, which is MACsec capable. Pretty straightforward, but definitely something worth considering. Customers always ask me, do I need to encrypt my traffic? And my answer is, if you're asking me that question, the answer is probably yes. So something to think about anyway. Okay, next up, we have expanded Direct Connect capability for local zones. So what we're going to be doing, this is a coming soon slide, so this isn't available yet, but one of the few coming soon things you'll see this reInvent, but we are expanding Direct Connect connectivity for our local zones. So a local zone is, again, similar to an outpost. It's built on the same technology, but we've essentially extended AWS regions out to other locations. For example, we've got our US West 2 region up near Portland. We've extended that region down to LA. You can deploy things in LA in the same VPC using a local zone. LA supports Direct Connect. We're expanding that Direct Connect capability to other local zones like Boston, New York, Chicago. So that's going to bring a lot more private connectivity into things like local zones in the future. Okay, that brings us to the next exciting thing we've got here, AWS Direct Connect Site Link. And so with Direct Connect, we have Direct Connect Gateway, and Direct Connect Gateway essentially is allowing you to connect through to multiple VPCs. And so what we actually did, and this was based on customer feedback on how Direct Connect Gateway works, we're now enabling the ability for Direct Connect Gateway to provide connectivity natively to your sites. So from site A connected via a Direct Connect to a Direct Connect Gateway down to site B. And so we'll have a look at what that looks like. So essentially, before SiteLink, you could essentially have a topology like this, where you've got two direct connects from two different sites, two on-premises, connected through to a Direct Connect Gateway. Notice we've got two private virtual interfaces. You've got a physical connection, a cross-connect, and a private virtual interface connected through to a Direct Connect Gateway, times two because you've got two sites here. Now, one of the data paths that we got asked about a lot was, hey, I've got site X and site Y, can't I just do this? I've got two circuits, why can't I just trombone through the Direct Connect? Unfortunately, that was what we call a disallowed data path. The Direct Connect Gateway was for transitive traffic through to the VPC only. So you could build instances inside your VPC and tunnel traffic and build an overlay. It gets quite complicated. But customers really wanted to use the AWS backbone that we've deployed for all of our Direct Connect POP locations. So now when you create a private virtual interface, you've got this additional option. Super, super simple. You enable SiteLink for the private virtual interface here. And what that's going to allow you to do is use that Direct Connect Gateway to allow that data path. And so if we look at this from a greater scale, essentially the Direct Connect Gateway, which is a global service, you can attach all of these private virtual interfaces to, and then use that for your backbone connectivity. And so quick photo there if you folks wanted to take a photo of that. Sorry, running a little quick there. But essentially it would look something like this, where you've got the Direct Connect POP locations, you've got connectivity through to the Direct Connect Gateway, but then all of your sites are connected to the Direct Connect POPs. And each of these sites can now talk to each other globally, because Direct Connect Gateway is a global service. Pretty awesome stuff. Now, if I was going to say there's one, or actually I think there's two themes for networking in this reInvent. I would say there's IPv6 and a whole bunch of the stuff that Alex has been talking about, but I'd also say global connectivity is the other theme that we're really seeing this year. So that leads me to, and Direct Connect Gateway is for all POPs except China, but this leads me to the next service. There's a quick QR code for SiteLink if you'd like here, if you want to take a quick photo of that. If you folks are using Direct Connect, I think SiteLink's just one of those things that, you know, instead of having an MPLS WAN backbone, you could use SiteLink for site-to-site connectivity. But that leads me to the next service, finally, AWS Cloud WAN. And so what we decided was, hey, we've got this backbone. We've spent a lot of time and energy and engineering work to build this amazing backbone. I mean, I've managed internets for small Asia-Pacific countries. I've seen a lot of network connectivity, WAN connectivity, MPLS connectivity, and the backbone that I've seen at AWS, I've never seen anything like it before in my career. So the backbone is amazing. And the idea here behind Cloud WAN is, how do we help customers use our backbone better? Let's dive in and check it out. So Cloud WAN is available in public preview, And so there's some disclaimers here. Cloud WAN is not something you want to be using for your production workloads today, but it is available in public preview. Jump in and check it out, and we do want to hear feedback on this. But the idea of Cloud WAN, or AWS Cloud WAN, is you can build global networks in minutes across the AWS backbone. So you're essentially using our backbone to build an overlay that is Cloud WAN to allow connectivity between your sites, between your VPCs, for hybrid connectivity. We'll talk about that. You can also build segments, which we'll talk about as well, to have policy across the backbone, to allow some sites to connect to other sites, but not others. So essentially, what Cloud WAN looks like is if we have multiple regions in this case, we've got region 1 and region 2, we might have some VPCs, maybe we've got an engineering VPC, we've got the internet, which you might want to connect to, we've got a sales VPC. We then might have some sites, so branch offices, data centers, maybe a group of branch offices, and they might be connected to AWS in various different ways. What we'll do then is create a global network, or we'll create a Cloud WAN global network. And this is basically an AWS managed backbone deployment for you to use based on the policy that you define through what we call Network Manager, which is a pre-existing service. But essentially, you create these policies or network segments, and here we've got shared services, engineering, and sales. And so each of these attachments or connections would attach to a different segment. So we've got engineering connected to the engineering segment, sales to the sales segment, etc. But you'll also notice that we've got our VPNs connected to these segments as well via VPN attachments. We've got Direct Connect Gateway in here as well. A bit of a disclaimer on Direct Connect Gateway. It's not available right now in Cloud WAN. It will be coming in 2022. I've got a couple of other things that we'll be releasing in 2022 as well. But essentially, we can then build network policies, and in 2022 as well, we'll be doing performance monitoring too. Okay, quick photo there if you folks want to grab that. Now we're running a little short on time, so I am going to go a little bit faster here for the remaining stuff here, and we have one more thing that I want Alex to dive into as well. If you folks don't mind sticking around for half a minute as well, we can dive in a little bit more here. But Cloud WAN essentially is going to allow you to have connectivity between VPCs, your WAN connectivity, or you might build a hybrid model like so, where you've got your on-premises and your VPCs all connected through this global Cloud WAN or global network. Really quick here, because this is what really helped me understand Cloud WAN. You've got a TGW and a TGW attachment. What you would do with Cloud WAN is actually remove a route and attach remove the route from the TGW attachment and send it to the Cloud WAN attachment. So it's very similar to Transit Gateway or a TGW. Okay, some quick differences here because we have SiteLink and Cloud WAN. Cloud WAN is really for VPC or hybrid connectivity, SD-WAN, you can do segments. SiteLink is more for port-to-port connectivity. So it doesn't depend on AWS regions, and I think that's the key piece there. And it does also support 100 gig connectivity. Both of these use the AWS backbone, support things like MACsec or IPsec, and are available globally. So a little bit of a difference there. They are similar sounding services though. And within Network Manager, we also have topologies, metrics, and events that you can see for your global WAN through Cloud WAN as well. Now this slide here, which Alex had up earlier, I just want to say that we do see a lot of customers doing this or wanting to do this kind of thing with a hierarchical TGW deployment. With Cloud WAN, you could actually remove all of that and just have a global network, and just have your policies and network segments within Cloud WAN. So it does greatly simplify things if you needed things like multiple transit gateways and that sort of thing. Okay. So the disclaimers, it is a public preview. It's not intended for production use. Jump in there and check it out. We're looking for feedback. Coming in 2022, things like transit gateway attachments. We'll be doing more performance monitoring, direct connect gateway attachments, etc. So there's a few things that we're still building, and that's hence why it's only a public preview. And a quick QR code there if you want to grab that as well. Now we do have a tiny bit more content for Alex on monitoring and visibility. Thank you.
Yep. I think this is the all networks, when it comes to monitoring and visibility, network engineers are like, okay, I need to do this something fast, right? So we have two services that we're going to focus on today. The recently announced Wednesday Network Access Analyzer that gives you visibility into all the paths in your network and to be able to understand how those paths are configured and why. And the second one is once you have all the paths, troubleshoot those that are not working as intended. So that is done with VPC Reachability Analyzer. Let's focus first on Network Access Analyzer, and we have a very little amount of time left. So what you can do with it is define your network access policy, run analysis, and understand what your network paths are and if they're fit according to your access policy. For this, there's multiple paths that can exist on your VPC, either internet connectivity, network segmentation, and access to private networks. Well, let's see how this works. And we're going to go through a very quick console rundown. We're going to create a network access analysis scope. You can do the defaults, or you can choose to create your own by editing a template. We're going to name our network analysis, and we're going to define the source and destination. For our source, we're going to try and understand the network access between a network interface and we do need to define it as a resource ID and our internet gateway. So if we go through the console and we configure all this, we are going to be able to review the JSON that is generated. We can change this, we can edit it, and we can thus visualize the network access analyzer scope. When we do this, we run the analysis and we get the information based on this analysis if there are any paths between our interface and the internet. We can see that we found two paths, and those are it. Scan the QR code for more information, and we have those paths. How do we troubleshoot them? Well, at the VPC level, we do have multiple constructs that play into the accessibility and reachability of resources. We have security groups, NACLs, route tables, and all these influence the paths in our VPC and outside our VPC. Now, what we want to do is once we've discovered all those paths with Network Access Analyzer is, try and understand why some of them don't work. And I've chosen here a path that doesn't work, and we're going to see why. With VPC Reachability Analyzer, we create this analysis, and we see that it's not reachable. And I bet that you're thinking, well, it's the security group, or it's the NACL, or it's the route table. What can it be, right? Well, our analysis says that it's not reachable because the interface does not have an elastic IP associated. So you can easily troubleshoot and you can understand why connectivity is not working appropriately. Scan the QR code for more information. And I know this has been a ride. Thank you. Please leave your feedback. And if you have any questions, do let us know. We can take questions outside because there's another session coming in. Do complete the session survey. We take your feedback to the heart. We're going to try and be a bit shorter next time. And thank you so much for joining us.
Thanks for coming, everyone.